the topic of this last movie, I'm going to take everything we've talked about, but I'm going to stop talking about neutral species, neutral diatomic molecules, and add and remove some electrons as the spirit takes me in order to talk about some ions. And you can actually see some fun little effects of adding and removing electrons associated with our MO theory that hopefully you'll get over these next 3 slides. So anyway, starting off with C2, this was the picture we drew before, bond order of 2. Now let's think what would happen if instead of C2 I looked at C2 minus, so adding an electron. Where does that electron go? Well, it will go into the sigma 2p. That's the next one up. So the electron configuration, sigma 2s2, sigma star 2s2, pi 2p4, and then sigma 2p1. Bond order will now be 7 over 2, which is 2.5. So in other words, adding an electron to a bonding orbital increases the bond order, makes the bond stronger. That's not exactly a big shock, is it? Add an electron into bonding and things get better. Now let's think about N2. Here's what the electron configuration of N2, 2s2, 2p3. Here's the MO diagram of N2. And of course, if you count up the bonding, 2, 4, 6, 8, minus the anti-bonding, 2. So 8 minus 2 is 6, divided by 2 is 3. Bond order of 3 and N2 exactly as we would expect. Now let's think first of all about N2 plus. What does that plus mean? It means we remove an electron. Where does the electron get removed from? Well, from the sigma 2p, because that's the highest filled orbital. So there goes an electron. So now electron configuration 2 in there, 4 in the pi 2p, 1 in the sigma 2p. Add it all up, bond order 2.5. So removing an electron from a bonding orbital, as we just did, weakens the bond, lowers the bond order, went from 3 to 2.5. Again, not exactly one of those wonderful wow moments, right? Take away an electron from a bonding orbital, you weaken the bond. But now instead of N2 plus, let's think about N2 minus. So here's our N2. Going to put another electron in there. Where does it go? Well, it has to go up here in one of the anti-bonding pi 2p's. So now there's the electron configuration. I'm not going to read it to you. Bond order now, we've got 8 bonding, 2, 4, 6, 8. But now we've got 3 anti-bonding, so the bond order is 2.5. So we added an electron, but it weakened the bond. It went from 3 to 2.5. Well, that's because we added it to an anti-bonding orbital. And in the same way that adding an electron to a bonding makes the bond stronger, adding an electron to an anti-bonding orbital lowers the bond order, makes it weaker. Now, as our last example, let's go back to the other arrangement of the orbitals in O2. The 2s and the 2p are far apart in energy, so therefore there's no silly mixing, so sigma 2p, then the pi's. Okay, here's the picture for O2, bond order of 2. We've already seen it before. I'll let you check it out if you wish at your own time. But now let's think about O2 plus. What do we have to do for O2 plus? Well, we're removing an electron, take away an electron from the highest energy orbitals, so one of those. So there's the electron configuration. We have 8 bonding, we only have 3 anti-bonding, so the bond order is 2.5. So in this case, we took an electron away, but the bond got stronger because we took it from an anti-bonding orbital. So you can actually explain some previously unexplainable issues associated with why sometimes cations are stronger bonds, sometimes anions are stronger bonds, simply by now explaining, are those electrons for the cations being removed from a bonding, which weakens it, removed from an anti-bonding, which strengthens the bond, or for an anion, is that extra electron going in a bonding, which is nice, or going in an anti-bonding, which is nasty. So half an hour on MO theory. When you get to university, if you study chemistry at university, you'll do a lot of MO theory, and hopefully this gives you a little introduction to it.